Welcome! In this session, we'll dive into problem number 457, circular array loop. This is a fascinating challenge that combines array traversal with cycle detection. Let's preview the problem, explore the requirements, and break it down step by step. Get ready to enhance your problem-solving skills. In this problem, we are given a circular array of integers called nums. Each value in the array represents the number of steps you move, either forward if the number is positive, or backward if the number is negative. The circular array wraps around, which means if you go past the last index, you continue from the first index, and if you move before the first index, you wrap around to the last index. This wrapping is handled using the modulo operation. Your goal is to determine whether there exists a single cycle loop in this array. For this loop to be valid, it must meet two key conditions. First, the loop must consist of at least two distinct indices, and second, all movements within the loop must go in the same direction, either entirely forward or entirely backward. If such a cycle exists, you return true, otherwise, you return false. The output of this problem is a Boolean value, true if there is a valid circular loop, and false if no such loop exists. Let's consider the first example to understand this better. Here, the input array is nums equals 2, minus 1, 1, 2, 2. Starting at index 0, you move forward 2 steps to reach index 2. From index 2, you move forward 1 step to reach index 3. From index 3, you move forward 2 steps to return back to index 0. This forms the cycle 0-2-3-0. This cycle is valid because it meets both criteria, it includes multiple indices, and all movements are in the forward direction. Therefore, the output for this example is true. In the second example, the input is nums equals -1, 2. Starting at index 0, you move backward 1 step to reach index 1. From index 1, you move forward 2 steps, which wraps around and brings you back to index 1. This forms the cycle 1-1. However, this cycle is invalid because it includes only one distinct index, which violates the requirement that a cycle must consist of at least two indices. Therefore, the output for this example is false. Now, let's look at the third example, where the input is nums equals 1, 1, 2. Starting at index 0, you move forward 1 step to index 1. From index 1, you move forward 1 step to index 2. From index 2, you move forward 2 steps, which wraps around and brings you back to index 1. This forms the cycle 1-2-1. However, this cycle is invalid because the directions are inconsistent. While indices 1 and 2 involve forward movements, index 2 then moves backward to index 1. This violates the unidirectional movement requirement, so the output is false. Finally, let's consider some additional edge cases. For instance, in a single-element array like nums equals 1 or nums equals -1, it's impossible to form a valid cycle because at least two indices are required. Similarly, if the array consists entirely of zeros, like nums equals 0, 0, 0, no movement is possible, so no valid cycle exists. Arrays with mixed directions, such as nums equals 1, minus 1, or nums equals 2, minus 2, also cannot form a valid cycle because the directions are inconsistent. Lastly, if the array contains very large values, ensure that the modulo operation is applied correctly to handle wrapping around the array bounds. These considerations help ensure that all edge cases are properly addressed when solving this problem. To solve the circular array loop problem, we need to determine whether a valid loop exists within the array. This loop must meet 3 key criteria. First, it should contain more than one element, single-element loops don't qualify. Second, the movement within the loop should be consistent in direction either entirely forward, or steps are positive, or entirely backward, or steps are negative. Finally, the loop must be circular, meaning that it wraps around the array when necessary. This wrapping allows us to treat the array as if it's connected end-to-end, so indices restart when they go out of bounds. With these criteria in mind, we can evaluate several approaches to find the best solution. The first approach we considered is the brute force method. Here, for each index in the array, we simulate the process of moving through the indices step by step to check whether a valid loop exists. To avoid revisiting indices during the simulation, we use a visited set to keep track of the indices we've already processed. However, this approach is inefficient, with a time complexity of O(n squared). This is because we perform a simulation for every index, and each simulation can take up to O(n) steps. For large arrays, this repeated work makes the brute force method impractical. Next, we have the optimized two-pointer approach, which involves using fast and slow pointers to detect cycles. The fast pointer moves at double the speed of the slow pointer, and if they meet, a cycle is detected. To ensure the cycle is valid, we verify that all elements within the cycle maintain the same direction, either entirely positive or entirely negative. Additionally, if no valid cycle is found starting from an index, we mark all elements visited during the check as non-cyclic to prevent redundant work. This approach is highly efficient, with a time complexity of O(n), since each element is processed at most twice, and it requires only O(1) space. While slightly more complex to implement, it avoids the brute force method's inefficiency. Finally, there's an alternative approach using graph representation. Here, we treat the array as a directed graph, where each index points to its next index based on the array's values. We can then use graph traversal techniques like DFS or BFS to detect cycles. However, this approach is less space efficient due to the additional memory required for graph representation in visited tracking, and it introduces unnecessary complexity for this specific problem. After analyzing the options, we selected the optimized two-pointer approach as the final solution. The intuition behind this choice lies in the effectiveness of the two-pointer technique for cycle detection in arrays. This method eliminates the need for additional data structures, making it both space-efficient and performant. By marking visited elements during the process, we also minimize redundant checks, ensuring that the entire array is processed efficiently. There are a few key observations that reinforce this strategy. First, a valid loop must maintain the same direction throughout either all positive or all negative steps. Second, each index in the array can participate in at most one cycle. Finally, clearing non-cyclic elements as we go reduces unnecessary work, further optimizing the solution. In terms of trade-offs, the two-pointer method is significantly faster than the brute force approach, with an O(n) time complexity compared to O(n squared). While it is slightly more complex to implement, the improvement in runtime justifies the additional effort. On the other hand, the graph representation method is not only more complex but also introduces higher space overhead, making it less suitable for this problem. Ultimately, the two-pointer approach achieves the best balance between efficiency and simplicity, making it the optimal choice for solving the circular array loop problem. In the circular array loop problem, our goal is to detect a loop in an array of integers, where the loop meets three specific criteria. First, the loop must consist of more than one element. Second, the movement within the loop must be consistent in direction, either all forward or all backward. Third, the loop must be circular, meaning we can wrap around the edges of the array. The array is represented as nums, where each index contains the number of steps to move forward, if positive, or backward, if negative. To solve this, we'll use a two-pointer approach with marking visited nodes to optimize the process. The first step is to normalize movement using modular arithmetic. By calculating the next index as current_index plus nums, current_index %n, we ensure the movement wraps around the array. If the result is negative, we add n to keep the index within bounds, making the movement circular. Once we have this, we can iterate through each index of the array to begin our traversal. For each index I, we start a new traversal and determine the movement direction based on the sign of nums, I. Positive values indicate forward movement, while negative values indicate backward movement. To detect cycles efficiently, we use two pointers, slow and fast. The slow pointer moves one step at a time, while the fast pointer moves two steps. Both pointers must move in the same direction, either forward or backward, throughout the traversal. If at any point the direction changes, meaning the signs of the numbers at slow and fast differ, we abandon the traversal and mark all visited nodes as invalid. If the slow and fast pointers meet at the same index, we check for a valid cycle. A valid cycle must include more than one element, so we ensure that slow is not pointing to itself. If the cycle meets the criteria, we return true. Otherwise, we continue the traversal and mark all the nodes visited during this path as invalid. Marking visited nodes is crucial for efficiency. By setting the values of these nodes to 0 or another marker, we ensure that the algorithm does not revisit invalid paths. This optimization ensures the algorithm runs in linear time. A few key insights help us solve this problem effectively. First, the direction of movement is critical. A valid loop must maintain the same direction throughout the traversal, which is why we compare the signs of nums, slow, and nums, fast. Second, the cycle length must be greater than 1, single-element cycles are explicitly invalid. Third, marking visited nodes reduces redundant work, ensuring that each node is processed only once, which brings the time complexity down to O(n). The input array itself acts as the data structure for storing traversal states, saving space compared to using additional structures like a visited set. This space-saving approach, combined with the use of 2 pointers, makes the algorithm both efficient and elegant. The slow and fast pointers are essential for detecting cycles efficiently. In terms of complexity, the algorithm operates in O(n) time because each element is visited at most twice, once during traversal and once when marking nodes is invalid. The space complexity is O(1) since no additional data structures are used, and the input array is modified in place. Considering edge cases is also important. For example, if the array contains only a single element, no valid loop can exist. If all elements in the array are 0, traversal ends immediately as there is no movement. For arrays with mixed signs, we must ensure that loops do not switch directions partway through. Finally, single-element loops are explicitly invalid and must be ignored. These considerations ensure the algorithm is robust and handles a variety of input scenarios effectively. To implement the solution, we start by iterating through each index of the array. If the current element is 0, we skip it since it has already been visited. For the traversal, we first move the slow pointer one step using a helper function called get_next_index. If the resulting index is -1, it means the traversal has reached an invalid state, so we exit the loop. For the fast pointer, we move it 2 steps by calling get_next_index twice. Again, if either step results in -1, we exit the loop. If the slow and fast pointers meet, we check for a single element cycle by determining whether slow points to itself after 1 step. If it does, the cycle is invalid, and we break out of the traversal. However, if the cycle is valid, we return true, indicating that a circular loop exists. At the end of each traversal, we mark all nodes in the current path as visited to prevent revisiting invalid paths. The helper function get_next_index calculates the next index based on the current position and direction. It ensures movement wraps around the array using modular arithmetic. If the calculated index is negative, it adds the array length to keep the index within bounds. The function also checks if the direction of movement matches the initial direction. If not, it returns -1 to signal an invalid state. The mark_visited function is used to mark all nodes in the current traversal path as visited. It starts at the given index and continues moving to the next index using get_next_index until it encounters an invalid state or a node that has already been marked. During this process, the value of each visited node is set to 0. These helper functions ensure the algorithm is both concise and efficient, enabling us to detect circular loops in the array with minimal overhead. Here, we start by defining the function circularArrayLoop inside the solution class. The goal of this function is to determine if there is a single, circular loop within the array where all elements in the loop move in the same direction. First, we calculate the length of the array, n, and define a helper function next_index to compute the next index based on the current index and the value at that index. This helper ensures the movement in the array wraps around using the modulo operator. Next, we iterate through the array using a for loop. If the current element is 0, we skip it, as it indicates we've already visited this index. We then initialize 2 pointers, slow and fast, both starting at the current index I, and determine the movement direction based on whether the value at nums, I, is positive or negative. The while loop is used to traverse the array, updating slow by 1 step and fast by 2 steps using the next_index function. During traversal, we check several conditions to determine if the loop should break. If either pointer reaches a 0, or if the direction of movement changes, we exit the loop. Finally, if the slow and fast pointers meet and the next step does not form a single element loop, we are close to confirming a valid cycle. If the conditions for a valid cycle are met, the function immediately returns true. Otherwise, we proceed to mark all elements in the current traversal path as 0 to prevent reprocessing these indices. This is done using a while loop, or we repeatedly calculate the next index from the current position, store it temporarily, and set the current position to 0. This effectively invalidates the visited path. Once the loop marking is complete, we continue to the next index in the outer for loop and repeat the process. If no valid cycle is found after checking all indices, the function returns false, indicating that no such loop exists in the array. This implementation ensures that we efficiently determine the presence of a circular loop while adhering to the constraints of the problem. Here, we begin by defining the circular array loop method, which takes an integer array nums as input. The length of the array is stored in n. To simplify navigation through the array, we define a helper function nextIndex that calculates the next index in a circular manner. This is done by adding the current value at index I to I, then ensuring the result wraps around within the bounds of the array using modulo n. Moving on to the main logic, we iterate through each element of the array. If the current value is 0, we skip it because it has already been processed. Otherwise, we initialize two pointers, slow and fast, both starting at the current index. We also determine the direction of movement based on whether the value at the current index is positive or negative. The direction is important because a valid loop must maintain the same direction. Inside the loop, the slow pointer moves one step at a time using nextIndex, while the fast pointer moves 2 steps. The loop continues as long as neither pointer encounters a 0, and the movement direction of both pointers matches the initial direction. If any of these conditions fail, the loop exits. Now, if the slow and fast pointers meet, it indicates a potential loop. At this point, we check if the loop consists of a single element. This is done by verifying if the next index of slow is the same as slow itself. If it is, we break out of the loop, as single element loops are invalid. Otherwise, we return true because a valid circular loop has been found. If no loop is detected, we proceed to mark all visited elements as 0. This ensures that we avoid revisiting them in subsequent iterations. Starting from the current index I, we repeatedly move to the next index using nextIndex, setting each visited index to 0 until we encounter a 0. Finally, if no valid loop is found after processing all elements in the array, the method returns false. This implementation efficiently handles the problem with n time complexity by ensuring each element is processed only once. To solve the circular array loop problem, we start by examining an example where the input array is nums equals 2, - 1, 1, 2, 2. First, we initialize the length of the array, n, which is 5 in this case. We define a helper function next_index, I, to calculate the next index in the circular array using the formula, I plus nums, I, %n. This ensures that the indices wrap around when they exceed the bounds of the array. The next step is to iterate through each index in the array, starting with I equals 0. At this index, the value nums, 0, is 2, which is non-zero, so we proceed. We initialize two pointers, slow and fast, both set to 0. Additionally, we determine the direction of movement based on the sign of nums, 0. Since nums, 0, 0, the direction is positive, and we are ready to begin detecting cycles. The process of cycle detection begins by moving both the slow and fast pointers. First, the slow pointer moves to the next index, which is calculated as next_index, 0 equals 0 plus 2, %5 equals 2. Simultaneously, the fast pointer jumps 2 steps ahead using the formula next_index, 0, which resolves to next_index, 2 equals 2 plus 1, %5 equals 3. At this point, we verify that both nums, slow, and nums, fast, align with the current direction, which they do since they are both positive. Continuing the process, we move the pointers again. The slow pointer now moves to next_index, 2 equals 2 plus 1, %5 equals 3, while the fast pointer moves to next_index, 3 equals next_index, 0 equals 2. Once more, the alignment with the direction holds, so we proceed. On the next iteration, the slow pointer moves to next underscore index, 3 equals 3 plus 2, % 5 equals 0, and the fast pointer also eventually lands at next underscore index, 2 equals next underscore index, 3 equals 0. Since slow and fast now point to the same index, a cycle is detected. To ensure this is a valid cycle and not a single element loop, we confirm that next underscore index, slow, equals slow. This check passes, so a valid cycle is found, and we return true for this example. Now we turn to another example, where the input array is nums equals, -1, 2. First, we initialize the length, n, which is 2 in this case. Moving to the first index, I equals 0, we see that nums, 0, is -1, which is non-zero, so we proceed. We initialize the slow and fast pointers to 0 and determine the direction based on the sign of nums, 0. Since nums, 0, 0, the direction is negative. Next, we move the pointers. The slow pointer moves to next underscore index, 0 equals 0 to 1, % 2 equals 1, and the fast pointer jumps 2 steps ahead, arriving at next underscore index, 0 equals next underscore index, 1 equals 1 plus 2, % 2 equals 1. At this point, we check whether nums, slow, aligns with the direction. However, nums, slow, is positive, which does not match the negative direction we are tracking. This breaks the cycle detection process. Finally, we mark all elements in the current path as 0 to prevent revisiting them. Starting with j equals 0, we set nums, 0, equals 0. Since no valid cycle was found, we stop here for this index. After processing I equals 0, we move to the next index, I equals 1. At this index, nums, 1, is already 0, so we skip it. With no further indices to process, we conclude that there is no valid cycle in this example, and we return false. Now let's analyze a third example with the input nums equals 1, 1, 1, 1, 1. As usual, we begin by initializing the length of the array, n, which is 5. Starting at the first index, I equals 0, we see that nums, 0, is 1, which is non-zero. We initialize the slow and fast pointers to 0 and determine the direction of movement. Since nums, 0, 0, the direction is positive, and we proceed to detect potential cycles in this array. To detect a cycle in this example, we move the pointers repeatedly. First, the slow pointer moves to next underscore index, 0, equals 1, and the fast pointer advances 2 steps to next underscore index, 0, equals 2. On the next iteration, the slow pointer moves to 2, while the fast pointer jumps to 4. Continuing this process, the slow pointer moves to 3, and the fast pointer moves to 1. Then, the slow pointer moves to 4, and the fast pointer moves to 3. Finally, the slow pointer returns to 0, and the fast pointer also ends up at 0. At this point, slow and fast meet, indicating a cycle. To confirm this is a valid cycle, we check that next underscore index, slow, equals slow, ensuring it's not a single element loop. This condition holds, so we have found a valid cycle. For this example, we return true. The time complexity of this solution is O, n, and we can understand this by breaking it down into its components. First, the outer loop iterates through each index of the array, so it runs n times, where n is the length of the array. Then we have the inner cycle detection step, which uses the Floyd's tortoise and hare algorithm. This algorithm, with its two-pointer approach, ensures that even in the worst case, each element is visited only once during the detection process. Additionally, there's a marking step that sets visited nodes to 0. This ensures that no index is processed more than once during the entire execution. Together, these steps guarantee that the total time spent on each index is constant, leading to an overall time complexity of O, n. Building on this, the total work done by the algorithm is proportional to n. Since each index contributes a constant amount of work during the cycle detection and marking phases, the overall time complexity remains O, n. On the space side, the algorithm is highly efficient, using only O1 additional memory. This is because the cycle detection relies on two-pointer variables, slow and fast, along with a few other integer variables to manage indices and directions. All of these variables consume a fixed amount of space, regardless of the input size. Furthermore, the algorithm modifies the input array in place to track visited nodes, eliminating the need for additional data structures. This in-place marking ensures that space usage remains minimal. The solution also avoids recursion or stack-based operations, which could otherwise increase memory usage. By staying entirely iterative, the algorithm keeps its space complexity at 1. To put this into perspective, consider the naive approach to solving this problem. A brute force strategy would involve starting at each index, simulating the traversal, and checking for cycles. This could require traversing the entire array for each starting index, resulting in n squared time complexity. Moreover, such an approach might use additional data structures, like a set or a Boolean array, to track visited indices, consuming n space. In contrast, the optimized solution processes each index only once and uses in-place marking, achieving n time an 1 space complexity. Now, let's analyze the algorithm across best, average, and worst cases. In the best case, where the array contains no cycles, the algorithm simply traverses the array once, marking each index as visited, giving it a time complexity of n. In the average case, we still expect each index to be processed exactly once, maintaining the n time complexity. Even in the worst case, where there is a valid cycle in the array, the algorithm traverses all indices once for cycle detection and marking, keeping the time complexity at n. A mathematical proof of the big O shows that each index is visited and processed at most once during the detection and marking phases. With n indices in total, the operations scale linearly. The space usage remains constant since no additional memory is allocated based on input size. Therefore, the algorithm is both time and space efficient, with overall complexities of n and 1, respectively. When solving this problem, there are a few common mistakes you should avoid. First, be cautious with single-element loops. If an element at index I points back to itself, that's not considered a valid loop because the problem requires loops to have more than one element. To fix this, always check that the cycle length is greater than 1 before validating a loop. Another frequent mistake is mixing forward and backward directions within a single loop. Remember, loops must be entirely forward or entirely backward to meet the problem's criteria. You can enforce this by using the sign of the current value to ensure all steps in a loop maintain the same direction. Finally, it's critical to handle out-of-bounds indices correctly. Since the array is circular, moving beyond the bounds requires wrapping around using modulo operations. This ensures that calculations like I plus nums, %n keep indices within range, preventing errors and maintaining the circular behavior of the array. Another issue arises when revisiting elements that have already been processed. This causes redundant calculations and can lead to inefficiencies in your algorithm. The solution is to mark indices as visited once processed, so you don't revisit them. Additionally, be mindful of infinite loops caused by self-referencing indices, where an element points directly back to itself. These cases can cause the algorithm to run indefinitely if not handled properly. The fix is straightforward: explicitly check for self-referencing indices and ensure they are excluded from valid loops. These two practices will not only make your solution more efficient but also help you avoid logical errors during implementation. When preparing for interviews, it's crucial to focus on edge cases. These might include arrays with all positive or all negative values, arrays with exactly one valid loop, or even arrays where no valid loops exist. Interviewers often test these scenarios to assess your thoroughness. Additionally, ensure you can clearly explain how you maintain direction consistency within a loop. This involves showing that all steps in the loop either move forward or backward. Optimization is another key factor. While a brute force solution might work for small inputs, strive to deliver an efficient O(n) solution, such as using the fast and slow pointer technique or marking visited elements. Finally, emphasize how you handle the circular nature of the array, particularly how you wrap around indices. This is a critical aspect of the problem and an area interviewers are likely to probe. This problem shares similarities with other well-known LeetCode problems involving cycle detection. For example, in LeetCode 287, find the duplicate number, you use a fast and slow pointer approach to detect cycles. Similarly, LeetCode 142, linked list cycle 2, applies Floyd's cycle detection algorithm, which is a classic technique for this kind of problem. LeetCode 202, happy number, also involves detecting cycles but in a mathematical context, while LeetCode 141 focuses on identifying cycles in a linked list. Additionally, let's consider an alternative approach to solving circular array loop, the brute force method. Here, you simulate the traversal of the array from each index to check for valid cycles. While this method is simple to implement and requires no extra space, it's highly inefficient for large inputs, as its time complexity is n squared. This makes it less suitable for scenarios with strict performance requirements. A more efficient solution is the two-pointer approach, where you use fast and slow pointers to detect cycles. This method provides n time complexity and uses constant space, making it optimal for this problem. However, it does require careful implementation, especially when ensuring direction consistency and handling changes in direction. Another effective technique is marking visited elements. By marking indices as visited during traversal, you can avoid redundant checks and speed up processing. This approach is also n in time and 1 in space, but it's important to have a clear strategy for resetting marks if you need to process the array multiple times. These techniques balance efficiency and simplicity, making them preferred choices for this problem in both practice and interviews. Thank you for joining today's walkthrough of the circular array loop problem. We reviewed the algorithm, its time and space complexities, and practical applications. Keep practicing and applying these techniques to sharpen your skills. Don't forget to like and subscribe for more content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!